Welcome back, students, to another difficult integral question.
Another one.
Yep, and this one is quite long, so let's get into it. Find the integral of 4 over x power 4 plus 4. This is a rational function. We check the difference in powers between the numerator and the denominator. Since it is not 1, then we know that this cannot be integrated to give the natural log function. And so our first step is to see if we can factorize the denominator. We can write it as x squared whole squared plus 2 squared.
Ah, man, only if we had an x term, we could have factorized this as a perfect square.
Well, how about we create that term ourselves? We add and subtract 4x from the equation. Now we can write the first three terms as x squared plus 2 whole squared, and what's left is minus 2x squared. In fact, we can further factorize this using the difference of squares formula. It becomes x squared plus 2x plus 2 times x squared minus 2x plus 2. We can put this back into the question.
That's amazing! And now we can do partial fraction decomposition.
So we separate the terms in the denominator and can write it like this. Here, a, b, c, and d are just some constant values that we need to find. Now, multiply both sides by x squared plus 2x plus 2 times x squared minus 2x plus 2. This helps simplify both sides and gets rid of the fractions. We need to find the values for the four constants now. One powerful way to do this is by inputting values of x into the equation that helps us get rid of some terms and form simpler equations. We can input x equals 0 first. The left-hand side stays the same. However, on the right side, all these terms become 0. That gives us 2b plus 2d equals 4.
What else can we input to get rid of terms? This just seems to be getting more complicated.
Indeed, this method is powerful most of the times, but this time it seems to be extra work since whatever value of x we input, we will not be able to get rid of any constant. Then we can expand the terms instead. We expand all the brackets and combine the like terms. Now we can compare both sides. The coefficients of x squared and x cubed on the left side will be 0. So, comparing x cubed terms gives a plus c equals 0, which tells us that c equals negative a. We should write down the simpler equations first as they give us more information to work with. The second simpler equation is by comparing the constant terms. So 2b plus 2d equals 4. Divide both sides by 2 to get b plus d equals 2. For the x terms, all unknown constants have 2 being multiplied with them, so that seems like a better option to compare next. 2a minus 2b plus 2c plus 2d equals 0. Divide both sides by 2 to simplify it. We know that c equals negative a, so by plugging that in, we can cancel the two a's out. This gives b equals d. We can use this to simplify the second equation, b plus b equals 2, and b equals 1, which means d equals 1 as well. Finally, we compare the x squared terms. Negative 2a plus b plus 2c plus d equals 0, and plug in the values for b and d as 1 and c as negative a. Hence, a equals 1 over 2, and so c equals negative 1 over 2.
Finally, partial fractions take so much time.
Right you are, but we're almost done. Input these values back into the main equation. We can split this integral into two shorter ones to make it easier. This can be done due to the linearity property of integrals. Then again, due to the linearity property, we can write this as 4 different terms. In the first and third terms, we will take the constant common and write it outside, so it looks simpler. We have 4 integrals to evaluate now.
What? We have 4 rational functions now.
Guess it's time to factorize again. We employ completing the square method. Simply add and subtract 1 squared, and the first 3 terms can be written as a square binomial. Do this for both denominators. Now we can rewrite the integrals. The second and fourth terms can be directly evaluated, as we can see here that it falls within the format of the integral of tan inverse. So we get tan inverse x plus 1 for the second term and tan inverse x minus 1 for the fourth term. For the other two terms, let's do u substitution to simplify them. Let's start with the first term. We take u equals x plus 1 du over dx equals 1. Hence, du equals dx. Now, since we need to get rid of all the x terms in this, we will rewrite the x in the numerator as u minus 1. So we have u minus 1 over u squared plus 1 times du. Then again, we can split this into two more terms, u over u squared plus 1 and 1 over u squared plus 1. The second one can be done directly using tan inverse, so it is negative 1/2 tan inverse of u. Plugging back in the value of u gives half tan inverse of x plus 1. Moving on. The first term lies in the form of the derivative of a natural log function, but to fulfill the requirements we multiply and divide this by 2. This way the numerator becomes the derivative of the denominator, as the derivative of u squared plus 1 is 2u. Hence, the integral is 1/4 ln u squared plus 1. Substitute back in the value of u, and expanding the brackets gives 1 over 4 times ln x squared plus 2x plus 2. All right, moving on to the third term. This is done in a similar fashion, so I will do this fast. U substitution with u equals x minus 1 this time, and du will equal dx. Hence the term is negative 1 over 2 times the integral of u plus 1 over u squared plus 1 du. Write this as two terms as well. The second one becomes negative 1/2 tan inverse of u, and in terms of x, it is 1/2 tan inverse of x minus 1. For the first one, we multiply and divide by 2 to get it in the proper form, and so the integral then gives negative 1/4 ln u squared plus 1. Plug back the values of u here as well, and then expand the bracket. All our terms have now been solved. Now we write all 6 terms together. The ln terms can be combined, and the similar tan inverse terms can be added, giving us the final answer 1 over 4 ln x squared plus 2x plus 2 over x squared minus 2x plus 2 plus half tan inverse of x plus 1 plus half tan inverse of x minus 1 plus c.
Wow! We just converted one integral into 6 and evaluated it.
I know, it's madness.